Hmm. Um, okay, so what was that? That was me driving a car honking at you. And what exactly did you hear? Well, if you were standing outside, you heard my very awesome car horn, and it changed sounds as it went by. I have a better demonstration for you. Just give me 1 second. Okay, so this will work a little better. Pretend you're outside. Wait, sorry. I want you to close your eyes. Pretend you're outside because we're almost allowed to go outside now. And, you can go outside. You're wearing your face mask. That's cool. And you hear a car coming down the road. And for whatever reason, that car is blaring its horn. Now, this is what you should hear. And you've all heard this before. Now, what I want you to notice, A, my eyes are still closed. And what I don't want you to pay attention to is the sound does get louder. Why does the amplitude or the sound get louder? Well, that's easy. The car is getting closer to you and then further away, so obviously you will hear the sound louder. You know I have my whistle. I don't know if I can do it with my left hand. If I come up behind you and whistle as loud as I can right in your ear, it sounds louder than if I'm further away because the amplitude will be louder. The wave hasn't lost its energy through the air yet. So we're not paying attention to the loudness, we're paying attention to the sound, the frequency or the pitch, and that frequency changes. So here we go, a way better example than me going meow. So what was that? That was the Doppler effect. And what we're going to talk about today is going to be focusing on the Doppler effect. Now, I will follow up with some Doppler effect math, but overall, we are talking about the Doppler effect, which is, well, I don't want to tell you what it is right now. I'm going to have somebody else tell you. Now, it's a 3-minute clip, and then I'm going to come back and talk about it just like I have in the past. And the gentleman has a British accent, so you know it is correct. Now, one thing I want to preface, we have been talking predominantly about mechanical waves, and we keep using sound waves. But all of the properties we've learned so far, and the ones we'll continue to learn, amplitude, frequency, wavelength, wave velocity, the Doppler effect, the new ones are going to be reflection, refraction. All of these wave properties are for all waves, not just sound waves and not just mechanical waves. Our next topic is electromagnetic waves, aka light waves. And those have some funky things going around, but the majority of the properties that we've learned all still hold true. And the video talks a little bit about light waves as well. Now, this part of the video is going to be your favorite part because it's the part that I'm not in. It's a 3-minute video that's going to explain the Doppler effect. Now remember, we already heard the car horn. Have you heard the Doppler effect in real life before? Probably. If you've ever watched like the Weather Channel or the news that tells you the weather, they talk about Doppler radar. So the Doppler effect, again, is not just sound waves or mechanical waves. The Doppler effect is any kind of wave, just like everything we've spoken about before. Now, this video does go into a little bit of light waves, but the main focus are sound waves and that meow sound that you hear. So let's get to it.
The Doppler effect. In Sheldon's words,
it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Did you get that? Probably not, but we'll get there. Don't worry about
it. The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense. But it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you. And a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
Now you can see I got my Doppler effect hat on, so I've changed so I can go really fast. I've reworded a little bit what Sheldon said. Sheldon says the Doppler effect is the apparent change in frequency due to relative motion of the observer. But I made it sound a little easier here. Here you can see it's the apparent change in a frequency of sound. I'm only talking about sound, but remember, all waves caused by the motion of either the listener, that's the observer, or of the source. So in other words, the car could be driving towards you, or you could be running towards the car. Now, the apparent change means it's not a real change, it's an observational change. In other words, if I am in the car singing, la, very pretty, that to me and everyone in the car sounds the same. That's the actual frequency, the actual wavelength. You, if I am in the car with my head out the window sticking towards you, you hear that as the Doppler effect. A high frequency to a low frequency. So you are the apparent change. It's an observational change. Now, let's get into it a little bit deeper. Before we move forward, I want to recap something that we should know. Wave velocity of any wave that we have studied thus far does not change in a medium. What does that mean? The speed of sound is approximately 343 meters per second in air all of the time. It does not matter if I talk really high or if I talk really low. The speed of sound is the same, 343 meters per second. Now I want you to think, what if it wasn't? If I were talking in all different sounds, then the speed would get your ear differently and it would sound all jumbled. So as soon as those words come out of my mouth, any sound, high frequency, low frequency, it is traveling to you at approximately 343 meters per second. The only way to change that speed is to change the medium, like when I sucked in helium or when I sucked in hexafluoride. To change the medium, if you go underwater, if you hit the table, those are different mediums. So once that is out in air, we can use our simple equation, velocity equals distance divided by time. But it's special in wave talk. A distance is specifically just a wavelength, which I have here, wavelength. 1 divided by time is a frequency, because time is in seconds or a period. So 1 divided by period is simply a frequency. So the wave equation, which you should have looked up previously, is velocity equals the frequency of a wave times its wavelength. That is nice and simple. If the speed of sound that we've been talking about is always staying the same, which means this is always 343 meters per second, that means as frequency increases, the wavelength must decrease. The velocity remains the same. Now that's going to be important when we talk about the Doppler effect. Now this is a similar picture to in the video. If you were standing here and there's a sound traveling towards you. Now we know sound waves are longitudinal. These are just easier to picture. The sound waves, because the waves are physical things in the air, they bunch up, which means you can physically hear, or in this picture, you can physically see that the wavelength, the distance from here to here, is smaller. So a small wavelength means a high frequency. So you hear a higher pitch. The speed of sound, 343 meters per second, remains the same. Now, after the car passes you, you can physically see this, or you'd physically sense it with your ears. This wavelength is further apart. That is, apparently you feel them or see them further away, which means a big wavelength is a small frequency, so you would physically hear a lower pitch. Now, it doesn't matter which thing is traveling. If there was a constant sound, la, and you were running really fast towards me, you would get to every wave faster. Thus, you would think that the wavelengths were smaller, and it's the same thing. If you're running towards the waves, small wavelength, high frequency. But that speed of sound, 343 meters per second, always remains the same. This is just a graph of what that shows. It's a simple graph where there's an object traveling towards you, right? Here's you. This is a frequency versus distance. As it gets towards you, this is what the actual sound is. Now you observe it change. You observe that frequency going from a high frequency to a low frequency as it passes you. Now, sorry, I didn't want that animated. Okay, the Doppler effect is when a source or an observer is moving. There is an observed change in wavelength and frequency. We hear or sense the frequencies in all waves, as in the video, sound waves and light waves. Light waves we'll talk about in a couple of weeks. The rest of this you should read and try and understand. We're going to talk about sonic booms in the future, but we now need to examine the mathematical stuff, the fun stuff. So, the Doppler effect has 4 scenarios. You can move towards the source, you can move away from the source source can move towards you, the source can move away from you. We're going to look at all of them. Now, lambda is our wavelength, f is our frequency, and v is our velocity. That is of the sound, or that is just our general concept. Now, we're going to say v naught is the speed of the observer. Vs is the speed of the source, because one of those two things is going to change. Now, if the source is stationary, it doesn't matter what side you are at, everybody hears the same sound. The observer and the source, we all hear the same frequency, they all observe the same wavelength, and again, that speed of sound, 343 meters per second, not changing in air. Now, what happens if you decide for some reason to run towards the car? Well, that's weird. Well, then there's a new observed velocity, v prime. Well, what is that? That is the speed of sound, v, plus the speed of the observer. So this would be 343 meters per second. Maybe you're running at 10 meters per second. So that observed velocity, you would think for some reason that the waves were traveling faster. 343 plus 10. The wavelength technically is remaining the same because that's being admitted by the source. You were just getting to each wave faster. Because you're getting to each wave faster, you would observe a different frequency, which we're going to call f prime. So doing some fancy substitution, I'm not going to get into that in super detail. We end up with a new equation. The observed frequency, what you hear, is the speed of sound plus how fast you are moving, so 343 plus 10, divided by, again, the speed of sound, 343, times f, the actual frequency coming from the car. Then you would hear a higher frequency. And if you just do that real fast, pick any number. Say 343 plus 10 divided by 343, and then multiply it by an actual frequency, 600 hertz. F prime will come up to be bigger. Or a higher frequency. Well, now what happens if that horn is really scary? So you run away from the horn. Run away from the horn. Well, V prime, again, is the observed velocity. The waves will take longer to get to you. So we have 343 minus 10 meters per second. You're running away. So our new equation is 343 minus 10, 323, divided by 343, multiplied by the actual frequency of the car, or of the horn. You're going to get a lower frequency, or a lower pitch. That is the F prime, or the observed scenario. Now, what happens if, well, this is more common, that car is driving towards you? Well, this is going to be a little bit of a different, the same concept, but a little differently. Again, if the car is driving towards you, you should hear a higher frequency, smaller wavelength. If the car passed you, you'll hear a lower frequency, or a lower wavelength. So let's take a look at the math. Now, because the waves are bunching up this time, we're going to play with the wavelength. So this wavelength prime is our observed wavelength. The actual wavelength minus the change in wavelength. So there's a lot of fancy math here when we get to the end, because we don't really have to derive equations. We have to understand what they mean. Again, if the car is moving towards the observer, we should hear a higher frequency. So, speed of sound, 343, divided by 343 minus the speed of the source. So if the source were going 20 meters per second, 343 divided by the whole, 343 minus 20, so 323, times the actual frequency, we'll end up with a higher frequency. It is the exact same concept. It's weird that it's a different equation, but it's the exact same concept. Again, I challenge you to try it. Now, the converse is true. We're not going to go through all the math, but if the car is moving away from you, you would observe a longer wavelength. Thus, you would observe a bigger wavelength, lower frequency. So here we would have 343 divided by a bigger number times the actual frequency would get the observed frequency, or a lower pitch. Now, you don't need to memorize all four equations. We have one general equation that works for everything, provided you are conscientious of your negatives and your positives. We have the observed frequency. This is what the observer hears. This is the actual velocity of sound, 343 meters per second. This is the velocity of the source, whether they're moving or not moving. This is, again, the actual velocity of sound, 343 meters per second in most cases. This is the speed of the observer, whether they're moving or not moving, away from the source or towards the source. And then this is the actual frequency. Now, just be conscientious. The sign of Vs and V naught depend on the direction. Always make same directions easy. To the right, positive, if I'm running away. If I'm going towards, go negative. So going to the right of the page is always going to be positive. Going to the left of the page is always going to be negative. And it doesn't matter who's moving, the velocity of the source or the velocity of the observer. Bam! That is all I have for you today. It was a lot. Hopefully take your time, take all this in. We're going to have a follow-up worksheet on this, on the concepts, and then on the math. Again, that's all I have for you today. If by some chance you're watching this on my YouTube channel, please feel free to like, comment, and subscribe, and you will see me next time.